Okay. Sharing my screen. That's nice. So, kind of review, kind of picking up from last day. What were we doing? We did a confidence interval for 2 sample proportions, right? And so, sorry, good morning. I hope you had a wonderful weekend. 2 sample proportions. I know I missed it. It was my dad's, well, it's my dad's birthday next weekend, but we did it this weekend. So I was down in Vancouver. It was nice, but not like here. So, oh well. Now 2 sample proportions. Now we're ready. Oh, sorry. We did a confidence interval, and just remembering that you're interpreting the difference in the proportions, right? And so what you can do is you can use any confidence interval to informally test the hypothesis, right? If the null value, so the hypothesized value, is inside the confidence interval, then you're, say, 95% confident that that's one of the values. So there's no reason to reject H naught, right? And then if the interval is outside that null value, right, on either side, then you have enough evidence to reject H naught. So that's kind of an informal test, hypothesis testing. And then we moved on to this hypothesis testing question, and I just brought it in from last day just as review. And so we'll work through this a little bit quicker. And I didn't quite get through it, did I? Not even close. That's okay. So do these data suggest that the proportion of all Americans, and I swapped the samples just because of how we had the information, who would be bothered a great deal by the melting of the northern ice cap differs from the proportion of all Duke students who do. And so we stated our hypotheses. What's really nice about 2 sample proportions, once you've identified that you have a 2 sample proportion question, then it'll always, the null hypothesis will always be that P1 minus P2. We talked about it doesn't really matter which one is 1 and which one is 2 as long as you're consistent, right? P1 minus P2 is equal to 0, right? So you put little question-specific subscripts on there. And so this will always be your null hypothesis. You can rearrange it if you want and just say that PUS is equal to P Duke, right? If you add P Duke over to the other side, or P2 in general, right? P1 is equal to P2. The reason I use this difference, even though P1 equal to P2 is kind of easier to wrap our head around, we're hypothesizing about the difference in proportions. And so it's nice to kind of see those there. And this is where we get our point estimate from as well, right? P hat US minus P hat Duke. And then that'll give us our point estimate. And our alternative hypothesis, the only thing that's going to change is, of course, the sign. And the sign depends on the question. Now, usually we're going to be talking about just, is there a difference between these two? Okay. And so the Americans, do they differ from how Duke students feel? And so then we have a not equal to 0. When you have a not equal to in your alternative hypothesis, then you don't care which extreme you're going into. So you don't care which tail you're going into. So we call it a two-sided or a two-tailed test, right? We keep that, right? We parking lot that all the way down until we need to find our p-value, right? When we're finding our p-value, that's going to be determined by the alternative hypothesis. The sign in the alternative hypothesis tells me which tail I'm interested in. And then we took a little detour just to check the conditions. Of course, the conditions, they're always going to check out. We just need to kind of know what has to be checked. Okay. And so highlighted. I added the hypothesis testing conditions. What's really nice is it doesn't matter if you're doing a confidence interval or a hypothesis test, these first two conditions are the same. So we have to have independence within the groups. So each sample has to be randomly selected. And we have to assume that the groups are independent of each other, which we can achieve by randomly sampling. So that's fine. So that's fine. Usually we have to assume that we've randomly sampled or we've actually randomly sampled. So both of those conditions are met by just randomly sampling. And the only kind of trickster one is the success failure condition. And so I call it the normality condition or the sample size condition. We have to have a large enough sample to be able to detect what we're trying to pick up on, right? If I'm trying to analyze a rare event, right, then we understand intuitively that I need to have a large sample in order to see some of those rare events, right? And so that condition is that we have to have at least 10 expected successes and at least 10 expected failures in both the groups. Okay, and so that's for the hypothesis test, whereas for the confidence interval, it was 10 observed successes and at least 10 observed failures in each group. And so the expected successes, we use the pooled proportion to check this condition. The pooled proportion was what? The pooled proportion was we take all our successes and all our failures. I'll kind of do an end of review or kind of this is the new stuff indicator. The pooled proportion is somewhat confusing. It's not confusing once you kind of know what's going on, but I know in the beginning it's confusing. We denote it by p hat. Context will tell you that this p hat is a pooled proportion because you're working in a two sample situation, right? Where you have p1 hat, p2 hat, and now you have this overall p hat. So if you think of it that way, then it makes a little bit more sense, right? And it stems back to the null hypothesis, right? We do all our testing assuming the null hypothesis is true. So if that's true, then it doesn't matter. Then I should be able to shove all these successes and failures into a pool and they should behave the same way, right? And so now p hat is the total number of successes in group 1 plus the total number of successes in group 2 divided by the total sample sizes, n1 plus n2. So here, this is the total successes. Can't do anything today over the total sample size or the total sample. Let's say. So we use our pooled proportion, and let me just snag the information that we had for this problem, right? It becomes a little bit hard to manage, at least in the beginning, because there's information from both samples, right? Sample 1 has information, sample 2 has information. Oh boy, here we're let's use this one. Copy. I think I used, okay, yeah. Got it. Got it, got it. There. Sure. So here was the US and here's the Duke students. Just highlight that. We have a sample size for each, and we found a sample proportion for each group. We rounded to 3 decimal places. Of course, if you're using Excel, you should just reference the cells and keep all those decimal places, and that'll be the safest thing to do. Okay? And so, but if you're working on paper, then it's nice to round some values, but I'll make a note here. Do not use rounded values in Excel, right? You're going to want to reference those cells so you can keep all the decimal places. Okay.
I had a question.
Oh, sure.
Say if a population was a decimal, like 1.5, or sorry, 1.4. You can't have 0.4 of a person. So
Right.
do you just round out to 2?
Do you mean these guys here?
Yes.
So those proportions will always be between 0 and 1. And then you can convert them to, sorry, I'm talking to the ceiling, but you're actually in my iPad. I hear you through the ceiling, so it's confusing. So here, these proportions will always be between 0 and 1. And so you can convert them to percentages, but you won't actually have to worry about rounding them. You'll want to keep as many decimal places as you can.
All right, thanks.
You bet. Okay, so from here, this pooled proportion, let's find this little guy. If we just had to take a step back though, this pooled proportion is a mashup of P1 hat and P2 hat, essentially. It's going to be weighted more towards the larger sample, right? So it's going to be weighted more towards the US, but it's always going to fall between these two proportions, right? And so that's one way of checking your work. Sometimes I see pooled proportions that are outside of these P1 hat, P2 hats, and just as a self-check, that doesn't make sense, right? So you'd want to go back and make sure that you've got it all sorted out. So in this case, P hat, well, I have the number of successes, 454 and 69, so I'm going to add those up. Over my sample sizes, which is 680 plus 105, right? So it'll be weighted more towards P1 hat, right? But taking into account P2 hat as well, and that's okay. Oh, let me grab my, I should do it on the Desmos calculator, but this one's so itty bitty, I'm just gonna do it on mine. 454 plus 69 divided by 680 plus 105. I get a pooled proportion of 0.666242038, which I'm going to round to. I'm only squishing it because I want it on the same page. Roughly 0.666. Did I say 3 of them? I don't know. Which we can check, right? This little guy is somewhere between 0.668 and 0.657. So that's good, right? It makes sense. And so this is the proportion if they were the same, right? If P1 is the same as P2 or essentially the same, then this would be a representative proportion. And so this is going to take the place of our hypothesized value. Okay, so now we're ready to check this condition. The condition was, let me just clarify, the normality condition was that I have to have at least 10 expected successes. What that's going to look like in each group, right? So I have to have N1 times P hat, because that p hat is what I use to find my expected successes. And so I have 680 times 0.666, which is definitely going to be larger than 10. Let's say 452.88, which is greater than or equal to 10. All of these will check out, right? And 2 times p hat, and 2 is 105 times 0.666. Which is 69.93, which is also greater than or equal to 10, right? And maybe I'll clarify here in each group. That's the only tricky part, is that you need to check it for both samples. Okay. And then at least 10 expected failures in each group. If these are successes, then 680 minus the successes must be failures, right? So instead of doing kind of fractional math, I'm just going to subtract 452.88 from 680 to get an approximation of my failures, right? Or you can do N1 times Q hat, right? Where Q hat is 1 minus 0.666. Oops, not divided by, minus 0.666, which is 334. So you could do that. Or you could say N1 minus, I'm just going to do it, 680 minus 452.88, which I'm feeling confident is also greater than or equal to 10. It's one of those things that takes me longer to write it out than to actually go through and check it. And 2 times Q hat is 105 minus 69.93. $35.07, which is also greater than or equal to 10. Okay. Therefore, we've checked all the conditions. The conditions for the central limit theorem apply. The conditions for the central limit theorem, CLT, apply, which we're happy about. Why are we happy about that? That's the reason we can use a Z, right, in our calculation, and we can use Z to find probabilities. And so that's the reason we're able to do all these things, all the things. Okay, so now we can go ahead and calculate Z. Now, I know I gave it to you last day, I hope, but step 2, do the test, do the do, or calculate the test statistic. You know, it's catchy. Technically, calculate the test statistic. I only mentioned that because for some reason last term, I guess I must have never called it the test statistic. And so then I got all these questions. It's asking for the test statistic, and I don't know what that is. That's when you do the test, calculate the test statistic. So now I'm trying to be better, saying both. The test statistic for 2 sample proportions is the point estimate minus the hypothesized value, right? But the null value is 0, so let's write that down. So it's always the point estimate, which in this case is going to be P1 hat minus P2 hat. Oops, that kind of looked messy. Minus P1 minus P2, right? How far is the observed difference in proportions from the hypothesized difference in proportions? Now this, we usually just write as 0, or we don't even write it at all, because we have to assume that the null hypothesis is true. We have to assume that these two are the same until I have proof otherwise. So that since the null hypothesis is that P1 minus P2 is equal to 0, this is equal to 0, and I'll say since that's our null hypothesis. And so that's always going to be 0. So usually if you write it out, I don't even bother writing it, right? I just use the point estimate in the numerator. But it's nice to highlight that you are still looking at how far is this point estimate from the null value, right? From the null hypothesized value, which is 0. Divided by the standard error. The standard error for hypothesis test uses the null hypothesized value, and so it uses the pooled proportion. So it's going to look like this: P hat Q hat over N1 plus P hat Q hat over N2, right? And I'll just highlight where P hat is the pooled proportion. I usually don't write it out this way because I don't like dealing with those fractions. What can I do? I have a common multiple here of P hat Q hat, so I can extract that to the outside, still within my square root, and I can get P1 hat minus P2 hat. Guess I don't need the brackets anymore. P hat Q hat times 1 over N1 plus 1 over N2. I'll say minus 0 up here. Usually I don't. So the differences are here, right? Do you want to do it twice? Now, if you're working in Excel, it doesn't really matter. What would you do? You would have your pooled proportion in one cell, 1 minus the pooled proportion in the other cell. It doesn't really matter which way you click through, right? You can make sure that they're the same. And so it's just, if you're working on a calculator, this saves you just a smidge of time. Yeah. Okay. Z, our test statistic, tells us how far, whoops, want to be in point mode, how far our point estimate is from 0, right? How far is the observed difference in proportions from 0? Anything more than 2 standard errors will likely reject H0, right? Because that's quite far away. And so what we have is Z tells us how far P1 hat minus P2 hat is from 0, right? Far in terms of standard errors, but just the general background is Z is always telling you how far your point estimate is from your hypothesized value. And so that's something that's good to keep in mind. All right, let's calculate our Z. Z is, and I'm going to use just the rounded values because I'm lazy. 0.668 minus 0.657. Oops. I'll keep the -0 there, but obviously you can drop it whenever you're ready. Divided by, and I'll use 0.666, which is the pooled proportion, times 0.334 times 1 over N1. N1 was 680 and 1 over N2, which was 105. Keep that all under the square root. Okay. Let's see if I can manage here. Where's my... So I had, oh, maybe I can do something cool. I always forget that I can do that. Okay, let's see here. So I'm going to start with the numerator, and I'm just going to call it P so that I can just use it later. And so in here, P is equal to, and I want to do 0.668 minus 0.657. I use P because it's a point estimate. Right? You wouldn't have to call it P in Excel, but I only have numbers on my iPad because I forgot my Apple ID password. One day I'll get there. Okay, so in the square root, we have 0.666 times 0.334. I'm going to do that. So that previous answer times bracket 1 over 680. Hey, 1 over 680. Oh my gosh. There. Plus 1 over slow and steady wins the race. There we go. And then I'm going to use that and take the square root of that little guy. So now my standard error is 0.05, let's call it, right? And so now I'm going to do P divided by that. Oops. P divided by the previous answer, and I get a Z of 0.2222, whatever. I'm going to take a screenshot and bring it in so I can blow it up. Oh, just do that. Let's see here. So my point estimate was a difference of 0.011. Now, depending on the spread, right, that could be very large or it could be very small. Now, our spread is 0.05 essentially, right? And so that's bigger than 0.011, which means that a spread of 0.011 is nothing, which is reflected in the Z score. So this is our point estimate, and this is the spread, right? The standard error. So it makes sense that we get a very small Z. Right? Visually, what does this look like? Z, now that I have a Z, right? This is my Z is roughly, let's use 0.2224. I don't know, can't stop, won't stop, there. Make a straight line. Z is centered on 0. Right? And it has a spread of 1. And we know just from the normal distribution that we have roughly 3 standard errors now, or standard deviations, until we run out of space under the curve. Technically, the curves continue on to infinity and negative infinity, right? But very, very low probabilities. And so now what happens is this Z of 0.222224, right, this guy here, is very close to 0. Telling me that, okay, close enough, right? These two values, so the difference that I saw is very close to a difference of 0, right? It's like saying, okay, here I'm sitting at the table, but then even if I moved out this way, I'm still sitting at the table, right? We've got this kind of realm where everything's considered to be basically the same, right? In fact, we tend to use a z of equal to -2 and +2 as kind of our cutoff points, right? Because then here I'm going to, so in this region, I fail to reject H naught. I don't have enough evidence to reject H naught. Do not have enough evidence to reject H naught. Whereas out here, right, I tend to reject H naught. I've moved far enough away. We call this the rejection region. That region is determined by alpha, right, the significance level, right? But in general, we use 5%, right? And if we think about 5% split evenly amongst the tails, well, that leaves 95% in here in the center, right? And so then we know from the 68, 95, 99.7 rule that, well, that's basically 2 standard errors away or standard deviations away. And so that's where that 2 comes from. So anything kind of ±2 in either direction, you're likely going to reject H naught. We like to have, so that's hard to communicate, right? Especially to a client. Oh, well, we were 0.22 standard errors away, so obviously we don't have enough evidence to reject H naught. That's hard, right? Because then you'd have to explain what standard errors are and what a mess. And so instead, we talk about probabilities, right? The probability of seeing this, if the null hypothesis is true, is this value, and that's what the p-value is. And so now, step 3, right? This is a formal hypothesis test, and so we have to use p-values. So find the p-value. The p-value is determined by the alternative hypothesis, right? Which tail do you want? Okay, and so here, we'll just kind of do a recall that the alternative hypothesis in this case, maybe I'll snag it. Copy. Call this, which means I have a 2-sided test. That's the biggest disconnect for people is, how do I know if I have a 2-sided or a 1-sided test? Well, you have to go all the way back to the alternative hypothesis, right? Just as a quick review, what are the possibilities? Well, you could have an alternative that P1 minus P2 is less than 0. Well, then you better hope that your observed difference is somewhere down here. Then this would be your p-value. Right? Or you could have P1 minus P2 is greater than 0. Same deal, but then you are interested in the upper tail, right? And we need to know which area we want, because in Excel, we can only get the area to the left, right? And then so you need to know if you have to do 1 minus, or if you have to multiply it by 2, right? And then in general, if the alternative is that P1 minus P2 is not equal to 0, then you take the area in one tail. Oh, I really smushed it there. Take the area in one tail and you multiply it by 2 times 2. And you kind of replicate it in the other tail. So more specifically for us, right? We have a two-sided test. We have a Z that's very close to 0, right? So for us, let's draw this out just so we can visualize it. Z is centered on 0, and I have some 0.2224. I can find the area in the upper tail, right? This is the one-sided p-value. Oops. How am I going to find that? I have to use the norm sdist command, right? And I can find the area to the left, but remembering that I want the area to the right. Yep. So I can use 1 minus the area to the left to find the area in the upper tail. Or what's a sneaky way of doing it? If you don't want to do the 1 minus, you can just make this negative, right? That's okay, because by symmetry, that tail is going to be the same as the positive tail. You just don't have to do the 1 minus. You have to negate your Z, right? But that might be nice. Save you just a couple of keystrokes, I guess. And then you'd have to multiply it by 2, right? So let's do that. Where's my numbers? Okay, well, that's from before, I guess. Let's see here. My Z, I'm just gonna enter it here. I should have calculated it here, obviously, and kept all my decimal places, but I don't like how what the screen does here, so it's kind of hard to work with. But so then here, my one-sided p-value, hey, it auto-corrected to value, that's okay, is going to be, now I'm gonna get better at doing this, but here we go, is going to be norm sdist. It's not exactly the same commands, but they have successfully emulated Excel, so close enough. And I want of this Z, I wonder if I have to tell it that it's true. Maybe not. This is the area to the left, right? And so what I want, I'm going to adjust this, but how? There. And I'm going to say that this is going to, hey, okay, I'll do it again. 1, no, come on. 1 minus norm sdist of this Z. That's going to give me the area to the left, right. Or what else could I do? We said I could do equals norm sdist of negative Z. Just make sure that they're the same, and they are, right? So either way, your one-sided p-value is going to be this. This is just the area in one of the tails, but you want the area in 2 of the tails, or both tails. It's only going to go into one of the tails always, so then it's your job to remember to multiply it by 2. So then this times 2. I get a massive p-value. I'm going to screenshot this and bring it in. How can I? Oh, well, I'll just write it on the side. Hey, where did it go? Done, save to photos. Good. Crop this up. Whoops. The differences here is the one-sided p-value. This was equals 1 minus norm dot s dot dist of z, right? This z here. Whereas this little guy, they're going to be the same, was norm dot s dot dist of negative z. Sneaky. And then this is our equals 2 times the one-sided p-value, referencing those cells. That makes sense, right? Makes sense in the way that, okay, the area in the upper tail should be relatively close to 0.5, right? 0 splits it in half. And so if I move out a little bit, I'm expecting it to be close to 0.5, but not quite. And so it's more like 0.4. That's great. Makes sense. And then I multiply it by 2, which means, okay, I would be just as concerned if that same thing happened in the other tail. And so now our p-value is huge. Our maximum p-value possible is 1, right? If our z was what? If our z was 0, right? Then the point estimate is 0 standard errors from the hypothesized value, then the p-value would be 1. Anything beyond that would be less than 1. Okay, so therefore, the two-sided p-value is roughly 0.824. Blah, blah, blah. Now, we use this to draw our conclusion. We already suspected that we weren't going to reject H naught, right? And so this jives with that suspicion. Why? Because our conclusion, if the p-value is small enough, then you have enough evidence to reject H naught. Or now, I can't remember if I have brought this in yet, but I think maybe it's time. Do I have it handy? Maybe not. I'll find it. Did I go in the right? I did. Copy. Make sure it copied. Just as a little, it's a little risque, I guess. But I find that it's helpful. If the p is low, then the null hypothesis must go. Just as a general kind of memory aid for your conclusion, right? Because what's it actually saying? If the p-value is small enough, then you have enough evidence to reject H naught. So here, this is actually saying if the p-value is small enough being less than the significance level, the alpha level. Oh, uh-oh. Less than the significance level, alpha equal to 0.05 by default, right? So if the p-value is low or small enough, less than the alpha level, right, then we have enough evidence. Then we have enough evidence to reject H naught. And I guess I should say in favor of HA, if I'm rejecting it. You don't have to say it if you don't reject H naught. In our case, well, to be small enough, has to be 0.05 or smaller, right, into those tails, right? And so now I have this huge p-value of 0.824, which means I do not have enough evidence to reject H naught. And so my conclusion, the phrasing stays the same from the one sample proportion scenario. So you want to highlight all the things you know, right? Since the two-sided p-value, right, you had to know that it was a two-sided test, and you know what the p-value is, so you may as well include it, right? And so you're just showing off all these things that you've used and that you know. So since the two-sided p-value of 0.824, I think, yeah, 0.824, and I use the phrasing that it either is less than the alpha level or it is not less than the alpha level, right? Just to narrow it down. And so it is not less than the alpha level, is not less than, and when I use 0.05, I'm just going to call it the assumed alpha level, right? Kind of the default, less than the assumed alpha level of 0.05, which means I do not have enough evidence to reject H naught. Which means I do not have enough evidence to reject H naught. Just highlighting here, it's not less than, so I do not have enough evidence to reject H naught. What does that mean in terms of the question that we wanted to answer? Oh boy, that's going to be a lot of scrolling. If I do not have enough evidence to reject H naught, the question was, do these data suggest that the proportion of all Americans who would be bothered a great deal by the melting of the northern ice cap differs from the proportion of all Duke students who do? Okay, we're just going to snag this, copy, and reword it as an answer. This question, right, reflects the alternative hypothesis, right? If we had these data suggest that the proportion differs, right, of group 1 differs from group 2, right, just kind of shorthand, that's the alternative. But we said I don't have enough evidence to reject H naught. And so this conclusion is going to be, okay, these data do not suggest that the proportion of all Americans who would be bothered a great deal by the melting of the northern ice cap differs from the proportion of all Duke students who do, period. Oops. All right. So you just reword the question as an answer, reflecting your conclusion that you just told me about. And I don't want to write that all out. Although it's quite a mess. That's okay. Okay. Any questions about two sample proportions? No? Okay. Good. We're ready to move on to 3 or more proportions. Oh, Emily, you didn't say it would be like this.
No.
On the plus side, 3 or more proportions, we only do hypothesis testing. So no confidence intervals. I know, I bet you wish it was the flip side. Confidence intervals, for some reason, are just kind of easier to wrap our head around. The math level is about the same, so it's not that. But for some reason, our brains do better with confidence intervals. Well, no such luck. So nothing to it but to do it, I guess. Here we go. What if we want to compare 3 or more proportions? Uh-oh. So we went from 1 to 2, and then 3 or more, they're all the same. And so kind of fun, because this is the first time that we're going to see a new test statistic, which I have a hard time saying. Test statistic. And it's the chi-squared. So here, the test statistic for comparing 3 plus proportions. I mean, you could use it for 2, but then it becomes a Z and kind of defeats the purpose. And so, so 3 plus proportions is called the chi-squared. And I emphasize that it's, and I should write it properly. You pronounce it chi, but it's really a Greek letter chi. Have you seen chi before in other, do you use it for kind of other notation? I'm thinking in wet, maybe not. But chi is a Greek letter X. And so it's kind of a snazzy X, and then we square it. And so this is called the chi-squared. Technically, it's spelled chi squared, but don't call it chi because it makes it sound like you don't know what you're talking about. You should call it chi. That's important. You don't want to sound like you don't know what you're talking about. All right. And so now we've got kind of 3 plus proportions. And let's see here. What could we do? I'm thinking about maybe snagging. No, I have no imagination. Recently, in recent times, my imagination is nil. Let's see here. Goodness of fit, blah, 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 blah. You know what? No, I don't want to use that. Nope. Go back to last day. I wish I had it handy. There's a clever, you know what? Let's go rogue. We're crazy like that. Unless you can think of some other proportions where you have 3 or more proportions. But the example that I don't know where to hunt down, so I'll make up my own version, is if you have a bag of M&Ms, right, then you have a proportion of all the colors, right? So unless you can think of some other, but I think that's kind of fun, right? I even had an old student email me one time, and she's like, I had a package of Mentos and it was all pinks. And I thought of you because I was trying to figure out the probability of it being all pinks in an entire package. She even sent me a picture of this magical Mentos pack. The probability is very, very low, right? Maybe we should talk about Mentos, the fresh maker. Like a 90s TV commercial machine. All right. So let's see here. To develop it, let's consider this example. I'll just make a simplified M&M example. Consider a bag of M&Ms. I'm not going to draw the ampersand. What a mess. With, what are the colors? Blue, red, and let's say green M&Ms. Green M&Ms. I know there are more, but let's just keep it simple for 3 colors, right? The same method applies for 4 groups, for 5 groups, 6 groups. But just to develop the idea behind the chi-squared, let's just focus on 3 groups. Right? And so here I have 3 categories. What if you want to know, so you have, let's keep it simple, you have 99 M&Ms. Why? Because it's divisible by 3, right? 100 would make a mess, but you have a random sample. You have a random sample of 99 M&Ms. If the M&M colors are evenly distributed, how many would you expect in each color, of each color, right? And so if the colors are evenly distributed, which is something that we're usually interested in, kind of an even distribution or some expected distribution is what we're going to work up to, right? So if the colors are evenly distributed, how many of each color, color would you expect? And I'll highlight here. This is our expected distribution, right? Or the hypothesized distribution. I would expect 33, 33, and 33. And so I would expect, let's see here, I'll put the color blue, red, and green. And I would expect 33, 33, 33 for a total of 99, n equals 99, right? Let's say, just as an example, just to kind of guide us there, what if you observed, what if I call this situation 1 and situation 2? We're going to have kind of 2 different observed scenarios. What if you observed, let's say, 30 and 28 and what's 99 minus 30 minus 28, 41. Total still has to be 99. Right? I guess I shouldn't have. This one's quite kind of far from 33, right? But what are we doing? We're looking at these, okay, these observed counts. Now 30, just kind of going with your gut, 30 isn't that far from 33, right? 28 is further, not that far from 33. But then this 41 kind of throws a wrench in things. And so what we're going to have is just the chi-squared is going to compare all of these observed values, comparing them to the expected values, right? And so maybe I should make the next one a little bit less extreme. Let's say this one is 31 and this one is 30, then, or maybe 32. 99 minus 32 minus 30. I'll make this 31. I just want them to be kind of obviously closer to 33. Right? We're okay with being a little bit under, a little bit over. That's all sampling error, right? You're not going to get exactly an even distribution every single time. And we're okay with that, right? But just like with the rejection region on the normal distribution, we have this kind of gut feeling of what's okay and what's not, right? And so for me, this 41 is kind of a little bit too far away from 33 to be considered, you know, close enough. And so here, right, this observed distribution, and I want to highlight that there's an observed distribution and an expected distribution. This observed distribution might be too far from the expected to be considered evenly distributed. Right? Whereas this second situation, right? And we're not going to work with the second situation because I'm more curious about this first one. But you can apply the same methods and see what you get for the second distribution. Okay? And so this one, we suspect this distribution is relatively even. Can do the test, right? But what is the test? All right. All right, all right, all right. What can we do? Let me just write out that we just, for 3 plus proportions, or I like to think of them as categories now, because we're going to be dealing with the raw counts. You can work with the proportions, but it's easier with the raw counts. So for 3 plus proportions or categories, we only do a hypothesis test, which means no confidence intervals. Kind of nice, but also sad. All right, so what are some things that we need to know? Well, let's talk about the conditions first, get those out of the way. The conditions for a chi-squared test, which is what we're about to do, are the conditions for a chi-squared test The chi-squared test is a hypothesis test. That's what the test comes from. So usually when we do a chi-squared analysis, we'll just call it a chi-squared test. The first condition is the same as always. We have to assume that all these counts or the observations are independent within the groups, but also across the groups, which I'll summarize as independence within and across the groups. Right. If we've randomly sampled, then we can assume that that's true. Random sampling satisfies this criteria. And maybe I'll call it this condition. Hopefully I said in my made up example that I randomly sampled. Oh, phew. You have a random sample of 99 M&Ms. What a relief. The second condition, which is different from, but not that different from the sample size condition that we've had in the past, is that we have to have at least 5 expected counts for each category. So at least 5. And I don't know why it's not 10 to match the others, but that's okay. At least 5 expected counts in each category. So for us, we had random samples, so we can assume independence within and between our samples or our categories. And we said, okay, if I expect an even distribution, I would expect 33, 33, and 33. So these are going to be my expected counts. Okay, so now I have 33 in each category, and so this condition is satisfied. I'll say we have 33 expected counts in each category, which is greater than or equal to 5, so that checks out. Okay. So if we're only doing a hypothesis test for a chi-squared, then I guess we better know what our null and alternative hypotheses are before we even do anything. So step 1 is to state the hypotheses. What are they? That's one of the key ingredients that you're going to need, even if you have to do a different type of hypothesis test, which is quite likely. We're going to go through all the basics, kind of the building blocks, but there are a lot of other tests that you could do. And so one of the main things that you're going to be after when you're researching other tests is, well, what's my null hypothesis and what's my test statistic, right? Step 1 is step 2. Your test statistic determines how to find your p-value. And then once you have your p-value, then your conclusion stays the same always, right? And so one of the things that we need is the null hypothesis. And for a chi-squared test, we're doing a chi-squared goodness of fit test. Okay? I know, it's terrible. I don't know why it's called a chi-squared goodness of fit, except goodness is a word, but it just doesn't work in this way. But goodness in the sense that how goodly does this expected count fit the observed count, right? And so in that way, it's a goodness of fit test. And you can adjust these expected counts, right, to whatever fit you're trying to hypothesize about. In this case, we're starting with the most basic kind of evenly distributed version, but we could have some other hypothesized proportions there. So this is a chi-squared goodness of fit test. And so the hypotheses for a goodness of fit test is that the expected counts, or maybe I'll start with the observed distribution. That can be the distribution of the counts or the proportions. It just depends on if you've multiplied by n or not. So the observed distribution is the same, right? And we mean relatively the same, right? We're allowing some wiggle room, but is the same as the expected distribution. This is generically the null hypothesis for a chi-squared goodness of fit test. And so what we want to do is we want to tweak this a little bit for our question, right? And so the observed distribution of colors, right, is evenly distributed, right? Our expected distribution that we're checking against is an even distribution. And so for us, let's say the null hypothesis is the observed, oops. Oh boy. Oh my gosh. One letter at a time. The observed distribution of M&M colors is evenly distributed. We're used to seeing our hypotheses being about parameters, right? Greek letters and things like that. But it takes some getting used to the chi-squared because it's all in words now. But that's just how it is. What's really nice is that there's no longer a one-sided, two-sided situation because of the shape of the chi-squared, which I'll show you. But the alternative is always going to be the negation of the null hypothesis. And so HA is, I'll just make a note here, negate H naught, right? And so the distribution, forgot a word. The observed distribution is not the same as the expected distribution. Isn't that nice? Right? So then our alternative, I'll just copy this. Copy. If we have evidence against H naught, then HA says that the observed distribution of M&M colors is not evenly distributed. Okay. Am I going to end on a cliffhanger? I don't want to. I'll just show you. Step 2 is do the test. Calculate the test statistic. Well, what is it? Here we go. Step 2, the chi-squared, thinking back to our Z, any test statistic is going to take the difference between the observed and the expected, right? The hypothesized value. So your point estimate minus your null value divided by the spread. It's going to be a little bit different because we're going to talk about the observed minus the expected. We square each of those, and I'm kind of building out from the center, divided by the expected count. And then we add those all up. Because each category is going to have an observed count, an expected count, and we square those just to make them positive so that they don't cancel each other out when I sum them all up. And then we divide by the expected count for each cell. And so I'm out of time, but that's the chi-squared. And just so you can kind of sleep on it, the chi-squared distribution looks like this, depending on the degrees of freedom, where it's always starting at 0. And so it's going to be a skewed distribution. And so the p-value, and I'll review this next day, the p-value is always just the area in the upper tail. And that's enough of that for today. If you have any questions, let me know. Otherwise, I'll see you on Wednesday. Let's stop this recording.